The Indian Association of Structural Engineers, also known as IAStructE, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IAStructE is registered under the Society's Registration Act 21 of 1860. IAStructE is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IAStructE has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Alok Bhaumik, Shri Manoj Mittal and Professor R. Pradeep Kumar as its president. IAStructE is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IAStructE has collaboration with various international professional like-minded associations and institutions. IAStructe's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IAStructE endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IAStructE is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IAStructe's activities are widely appreciated and known for quality technical contents. IAStructE is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, and a monthly newsletter. IAStructe's publications are becoming popular with time. IAStructE has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IAStructE started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IAStructE is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. IAStructE has its student chapters in several leading engineering institutions as well. Membership of IAStructE is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IAStructE is available on its website www.iastructe.co.in.
Vikas, shall I proceed?
Yes, sir.
Dear friends, welcome to attend this webinar. Today's topic of the webinar is Seismic Design Provision of National Building Code of Canada. I'm happy to introduce the speaker, Dr. Jagmohan Humer. He graduated way back in 1958 from Banaras Hindu University, obtaining distinction. Thereafter, he did his master's in structure from IIT Kharagpur again with distinction. And based on 59 exams of UPSC, he joined Class 1 service and joined CPWD in 1960. In 71 to 74, he went to Canada and underwent his PhD program in Carleton University. He came back, worked in the department for a year, and thereafter he got teaching and research assignment from 1975 in Carleton University. Present Dr. J.L. Humer is a renowned professor emeritus at Carleton University. He is a renowned expert in structural dynamics and earthquake engineering. He is key contributor to Canada's seismic design provision NBCC 2005 to 2020. He has authored over 144 research papers and widely used textbook dynamics of structures all over the world. His expertise has shaped major projects, including the seismic rehabilitation of Canada's Parliament building. He is honored with Order of Canada and numerous awards. The Indo-Canadian community recognized him as one of the jewels of India in Canada. Regarding the abstract of the topic, important topic, the National Building Code of Canada outlines seismic design provisions to ensure building safety during earthquakes, updated every 5 years. The latest version of NBCC is 2020, sets requirements to prevent collapse while allowing some damage. Post-disaster and high-performance buildings like hospitals and schools have stricter standards. Seismic hazards varies across Canada and is defined using uniform hazard spectra. Seismic forces are determined through dynamic analysis methods, including modal response spectra analysis and time history analysis. His presentation will cover the seismic design aspects of NBCC 2020. Now I request Professor Humer to kindly proceed.
Thank you, Dr. Dhawan, for that kind introduction, and thank you to the Indian Association of Structural Engineers for giving me the privilege of speaking to you on a subject that may be of mutual interest to all who are listening, especially to people who work in the area of earthquake engineering, in fact, to all civil engineers. What I will do is I'll talk about the seismic design provisions of the National Building Code of Canada, and I'll use my shared PowerPoint presentation to help me present this topic to you, at the end of which you may want to ask any questions. I'll try and answer you promptly, but sometimes it may be too specialized, in which case it may take some time for us to find out the real answer. So let me try and share my screen and start the presentation. Okay, so the National Building Code of Canada, the latest version of which is 2020, and it deals with a number of things, as I will mention, but I'm going to focus on the seismic design provisions. So as I said here, the NBC sets out technical provision for the design and construction of new buildings mainly. And it is these provisions are described in Division B of the code, which is entitled Acceptable Solutions. These provisions address the objectives of structural safety and structural protection when exposed to any of these forces, dead and live loads, wind loads, snow loads, and earth loads. NBCC is a model code, really, and it is only when the provinces of Canada adopt it that it becomes a legal document, becomes a set of regulations which all engineers, designers, those involved in the construction have to abide by. This presentation that I'm going to make highlights the seismic design provisions of NBCC. They are described in Division B, which is titled Acceptable Solutions. Part 4 of that in Section 1 and Subsection 8 of the code. So the title 4.1.8.1 refers to Part 4 of the code, Section 1, Subsection 8, and from 1 to 23 are referred to as articles. So we are going to go through these articles, not all of them probably, but most of the major articles from 1 to 23, which describe the provisions of the National Building Code and how they are used in design and construction. Now, what's the primary objective of the seismic design? What we want to do is a normal building to provide life safety protection to its occupant as well as to the general public who may be outside the building when the building is subjected to a ground shaking caused by a rare earthquake, and that's important. We have to define what kind of earthquake we are designing for. And a normal building is designed for an earthquake that has the probability of being exceeded once in 50 years. Or a return period of 2,475 chances, referred to as the design ground motion. Now, when I say once, a probability of being exceeded once, the chance is really 2% of being exceeded in 50 years. And the return period works out to 2,475 years. That's the design ground motion. All normal buildings are designed for this design ground motion according to the provisions of this code. Now, it is expected that the building might experience extensive structural and non-structural damage. We are not aiming to keep the building completely untouched because that would be really too expensive for a normal building. Some special buildings we might do something more than what we do for normal building. But during DGM, it is expected that the building will experience extensive structural, non-structural damage, but it will not collapse. It will not jeopardize life safety of those who are occupying the building or those who are public who are generally going outside the building, for example. Okay, so how do we achieve this high degree of safety? Let me The high degree is achieved through keeping the inelastic energy dissipation capacity in a ductility capacity, which is called in the structural force resisting system. And we'll use the SFRS as a short form for structural force resisting system. How do we develop this ductility? Is when the design and detailing contained in the code. You may be reinforced concrete, you may be steel, you may be masonry, or you may be timber. There are requirements within the code and even more than within the code, to the reference to standards of design. For each material, there is a different standard. And these standards will describe how do you achieve this inelastic dissipation capacity in each structural type. We can also enhance the security and the safety by making sure that buildings are regular in both plan and elevation. And whenever there is irregularity in the building, we have to have some additional requirements. These days, of course, hardly any building is regular because the architects and the designers want to exercise their freedom to produce a building which is both functional and aesthetic. And in that doing that, they often violate the conditions of regularity. And so the structural engineer must be ready to address those situations. Okay, there are certain categories of building, such as post-disaster buildings, just as hospitals, water and sewage treatment plants, and high importance buildings, which are used to be occupied in the case of a disaster or after an earthquake has taken place as shelters, such as schools and community centers. In such cases, the seismic design requirements include limiting the damage caused by the DGM level ground shaking. There will still be damage, but we want to limit that damage so that the building can either be functional or will be possible for it to be occupied. For example, post-disaster buildings are expected to remain functional immediately following an earthquake. So one should be able to enter and carry out all the expected tasks that a post-disaster building requires, a hospital, for example. In addition, they must satisfy requirements related to the force induced by a lower level earthquake with 10% probability of exceedance in 50 years. As I said earlier, normal buildings are designed for 2% in 50-year earthquake. But post-disaster buildings have some additional requirements which they must satisfy under a 10% probability of exceedance in 50 years. Similarly, high importance buildings which are used as shelters during and after an earthquake, such as in schools and community centers, they are expected to be safe to occupy after an earthquake. So they also must satisfy additional requirements related to a lower level earthquake that has a probability of 5% of exceedance in 50 years. So 2, 10, 5, 3 different probability levels. Normal buildings, 2%. Hospitals, 10%. And importance buildings, 5%. Now, as you probably all know, Canada is the second largest country in the world next to Russia. It's an area of 10 million square kilometers. And the seismic hazard varies widely across the country. So you need to quantify this hazard. And in Canada, the task of quantifying the hazard belongs to the Geological Survey of Canada, which is the department within the Ministry of Natural Resources of Canada, so-called NRCan. And that GSC is responsible for determining seismic hazard across the country. And how do they do that? There is the data that they have collected, GSC and its predecessors, over a period of 100 years or more, seismic hazard data, the magnitude and recurrence relationships for seismic events over the last 100 to 150 years. And basis of that data and the analysis of data in a probabilistic seismic hazard analysis, it provides you the seismic hazard at any site in the country. Just for an appreciation of this way the hazard varies, this is a map of Canada. And from the point of view of earthquake, you can design into 3 parts: the west, the east, and the middle part. And the middle part, which is shown in green here, is stable, hardly any earthquakes, very small quantity of earthquakes of low magnitude. West is the most active. As you can see from the magnitude dots, the large circles that you see, high magnitude, 7 magnitude earthquakes over the last 100 years are shown in the western side, which is Vancouver, British Columbia, those areas. So any building, any structure that is built in these areas is vulnerable. Even the east is also, there is a vulnerability on the north side, but not as much as in the west. So we have to define particular zone or particular point or whatever you are looking at, what kind of hazard it has. So this data that we've collected, or GSE has collected over the last 100 or more years, it allows the determination of earthquake magnitude recurrence relationships. Now, it's important to know that the seismic hazard at a site depends on 4 major things. The source zone, how far is the source where the earthquakes can take place, or how far is it from your site? And there may be more than one source zone, but you have to look at all of them. Now, what is the magnitude recurrence relationship for the source zone? Say, for example, magnitude 7 earthquake, how often does it happen? That's so-called magnitude recurrence relationship. How far is this source zone from your site? And what are the site properties that you are looking at for your site? Now, if you know these 4 bits of information, then we use what is called ground motion models, or GMMs. They are used to express the hazard in terms of what is importantly called as uniform hazard spectra. And I need to define that more carefully, because that's an important aspect. So what does the uniform hazard spectra do? It provides the mean values of the spectral acceleration, which has uniform probability of accidents. And it provides these values at selected vibration periods of the building. For NBC, these periods are 0.2 seconds, 0.5 seconds, 1.0 seconds, 2 seconds, 5 seconds, and 10 seconds. So these are discrete values that we are given. And later on, we'll see how if your period of the building is somewhere in between, you have to interpolate. And how do you do that? It also provides the information, the seismic hazard information also provides the peak ground acceleration and the peak ground velocity. The spectral acceleration is represented by a symbol SA, spectral acceleration, for a period T, and for site class X, we will define what X is. T is the period and X defines the site property. So what is the uniform hazard spectrum? It gives you the spectral acceleration for a system with 5% damping induced by this DGM, the design ground motion. We want to find spectra for different probability of accidents, 2%, 5%, 10%. And as I said earlier, normal buildings we are designing for 2% in 50-year earthquake, post-disaster buildings for 5%, and high importance buildings for 10%. The design spectrum is then constructed from this uniform hazard spectra, as we'll show in the next figure. So this is, first of all, you find out the SA values, design spectral acceleration values from the survey that we just did, or probabilistic hazard analysis. For example, SA 0.2 to SA 10.0, period 0.2 to period 10.0 for site class X. In this particular case, what I'm showing is for site class X, which is X has a value 760. And we'll talk about this a little later on, what this X really is. So it's also called class C. And this is for Vancouver. So the value of design spectral acceleration at those periods of 0.2 is given, 0.5 is given, 1.0 is given, 2.0, 5.0, and 10.0. These are discrete values that are shown here. So for example, this is for 0.2 and less. This is for 0.5. This is 0.1. This value is for 2. This value is for 5. And there is value for 10. I have not shown here. You in India you use similar spectra, but except that this is a smooth curve 1 over t in the middle range here, and there is an upper plateau, and there is a lower limit also given in the Indian National Code. So this is the uniform hazard spectra. When I say uniform hazard, that means these values which are shown in the right-hand column of this table have been derived for an earthquake with 2% accidence probability in 50 years. Just to show you some variations, this is the value of SA is 0.2 across the country for a probability of accident 2 years, 2% in 50 years. And for site designated as X450, and you'll see very high areas, high earthquake hazard areas in red. And as you go in the middle, the plateau, in the middle, there is not much seismic activity, and the values are pretty low, anywhere from 0 to 0.1 or so. This is the variation of 0.2 as SA 0.2 as an example. This is another map showing the variation of SA 1.0, which is much lower, of course. Now we'll talk about that X value that we have been referring to earlier. The ground motion models that we use to calculate the hazard include the impact of site properties. And the properties of a site are expressed as XV, sub V, and it is determined using the average shear wave velocity in the ground, top 30 meters, calculated from in situ measurements in the top 30 meters of soil profile below the foundation of the building. Or if measurement of the shear wave velocity is not made or is not possible, then by what is called XS, where S is a site class determined from either average standard penetration resistance, and you all are probably familiar with that, N60, or the average undrained shear strength, SU, in the top 30 meters of the ground profile. So you either use the shear wave velocity or use N60. Shear wave velocity is preferred, it's more precise. Now, let's look at what is XV and what does it show. So here is an example. First of all, if VS30 is greater than 760, but if the ground profile contains more than 3 meters of softer soil between rock and the underside of the footing or mat foundation, you cannot designate, even if it's more than 760, you do not use 760. You have to use 760 as the upper limit, as long as there is any softer material, because that makes it more vulnerable. If VS30 is greater than 140, but it has got all those ground profiles which are plasticity index greater than 20, moisture content greater than 40%, undrained shear strength less than 25, it's a very poor soil, soft soil, then you call it XE, E class, and we'll deal with class later on. But we don't now give V value because there's no purpose in giving V here because of the very soft soil. Similarly, if the ground profile contains all of those things, the liquefiable soils, more than 3 meters of peat, more than 8 meters of highly plastic soil, or more than 30 meters of soft to medium clay, then it's even worse type of situation, and we give it a classification called XF. So those are the things where even if you have measured velocity of shear wave in the top 30 meters, you do not use those values. We give them either XF or XE. And if it's more than 760 but has got these 3 meters of soil, we'll call it X760. Even if it is 800, we'll call it X760 because of the 3 meters of soil. So these are 3 exceptions. And let's not deal too much time on this one. This is a variation of hazard with VS30 for Vancouver. And these curves, for example, show the value of SA 0.2, 0.5, 1.0, and 5.0. All of these curves show you a 2% 50-year hazard in G. SA is given on this side. And as the value of the velocity becomes higher, the value of the hazard goes down, as you will expect. Okay, so the other situation is when the VS30 from in situ measurements is not available. What do? We'll call it a site designation XS, where the S is the site class determined using either the average standard penetrating resistance or the undrained shear strength. And the details are in here, for example. Now, class A, B, C. Now we got to those classes A, B, C, D, E, F, up to F. Now, if you look at this, you see a column which says VS30. That doesn't mean that we have measured VS30 in the site. There may be similar sites from which measurements have been done, and our site may resemble them. So these are off-site measurements if we have them. You may not have them, then that column doesn't exist. But we do have the average standard penetration resistance. We have the average undrained shear strength. In those cases where you have, obviously from comparing the sites, you see it's really very high shear wave velocity on a similar site. We don't need to worry about N60 or SU. We'll just simply call it class A or class B as shown here. But if you have values which are between those, we have very dense soil and soft rock, we'll use any one of these to classify the soil as class C, either greater than 50, SU greater than 100, then we'll call it, yeah. So you do use any of these three criteria. If you're confident that you have a similar site, you had a measured value of VS30 between 360 and 760, our site is similar, we call our site C. Or if you don't have that, we will go to this average penetration resistance and we measured value greater than 50, we call it class C. So those are the ways, and similarly we do that for D, E, and F. So so-called stiff soil, soft soil, other soil. Now there are, of course, similar classifications in the Indian standard of different kinds of soils, hard rocks, soft and medium type, and poor. Not exactly the same way they are defined, but they exist there. Okay, so how do you then find the seismic hazard in Canada? The seismic hazard for a given site is expressed in terms of uniform hazard spectrum, as I said earlier. And you simply go to a tool that the Geological Survey of Canada has produced, which is given in that link. And you will have a link of this when you see the recording. You can click on that link and provide information. Where are you located? What kind of soil you have? And you get the values of all of the spectral values at those selected periods. For example, I did this for a specific case of Vancouver. So I provided these values to that link. I said code edition is NBCC 2020. I can get values for 2015 code as well if I want to. My site designation was X760. So I provided that. My Vancouver is my city that I'm looking for, and its latitude is 49.25, and its longitude is minus 123.1. Alternatively, if I don't know the latitude and the longitude, but I know the address of my site, you give that address. For example, where I am sitting is 3 Huntwood Court. If I provide 3 Huntwood Court, it will automatically locate that on the map and calculate the latitude and longitude And that's all that matters. So those are the 4 bits of information: code addition, the site designation, and the latitude and longitude of your site. So you got the site type, XV, you got your location, and you got the code. These 3 things you supply to that link, and the link will produce this result as shown in the last table there. NBC 2020, 2% in 50 years. Values of SA 0.2, SA 0.5, SA 1.0, SA 2.0. These are all for X760 because that's what I supply. The values grow from 0.838, and they are in terms of G, of course, 0.838 to 0.321. The other day, I tried to compare these with the values given in Indian standard for the highest zone, and these are much higher than the values given in the highest zone for India. Seismicity of Canada is perhaps higher, and so the 2 things you can compare it always. Yeah, Z by 2 into SA is what the Indian code gives. It also gives you the values for 5% in 50-year earthquake, as well as the 10% in 50-year earthquake. Obviously, we need them for high importance building and post-disaster building. So this is also provided to us. Okay. So how do you find the values for intermediate values of the period between, say, 0.2 and 0.5, or between 0.5 and 1, between 1 and 2? You usually are asked to do log-log interpolation for over the period. And that's the preferred way. You can do linear interpolation, but there will be some error. Log-log interpolation will give you the best results. One specific case here is shown between 2 and 5 seconds. I did a log-log interpolation for 4 seconds, and I ended up with this value 0.0404. Okay, as you can see, it's between 0.113 and 0.029. And similarly, values are given for 10% in 50 years. All of that was produced by that link that we just talked about. And when you have time, go play with that link, and you will be able to get results for whatever latitude and longitude you wish to. There are certain parameters that we need to talk about. They are used in the seismic design, and these are important parameters. And similar things exist in the Indian code. Several parameters. These are used to trigger special provisions and restrictions in the design. And these are importance factors, seismic categories, and irregularity types. These 3 are very important in design, as we'll see in a short while. So NBC identifies 4 importance categories: low, normal, high, and post-disaster. And we will see later in table 3. It provides an importance factor for each of these. Now, this importance factor will be used in finding out the design shear or design force for the building. Okay. And you provide a higher importance. That means you design for a higher force. That means you design the building to have low ductility requirement. The higher the value of I, the less ductility is required. So importance factor I greater than 1 is intended to reduce the ductility demand on high importance and post-disaster building by increasing the force level that the yielding elements are designed for. So it's the same thing in the Indian code, where the factor R, which divides the elastic shear for ductility, is reduced by IE. So those are some values for the importance factor: low 0.8, normal 1, high post-disaster 1.5. The hospitals will have high E equal to 1.5, for example. Seismic category is another thing that is used to trigger certain requirements. Whenever there is these values, for example, if the value of IES 0.2 is ranging between 0.2 and 0.35, and IES 1.0 is ranging between 0.1 and 0.2. Then you have these two values. If both of these are satisfied, then it's category SC2. Higher these values, higher the category. So the risk is more. This is more risky than this one because there is a high values for S. So it's category 3 building. So if your building is located in these zones, then it's a category 3 building, and so on. If it is in this zone, it's a category 4 building. And these are used to define certain limitations on the methods of analysis, and certain restrictions are triggered by these seismic categories. The higher the risk faced by the building, the more restrictive the design becomes. They were introduced in NBCC 2020 as recently as that, as a simplified way to apply a trigger based on importance modified design accelerations. Now, the last one that I mentioned was the irregularity. This is very important for structural design of buildings. If a building is irregular, it is more vulnerable, and you have to take special care in designing this. So any of the features that we list in the next table, table 5, are designated as irregular. The Indian Code 1890, I believe, is also defines different irregularity features and gives you diagrams to illustrate what those irregularities stand for. So structures designated as irregular must satisfy certain provisions that are referred to in the code. As an example, if you have type 6 irregularity, which means discontinuation in capacity or a weak story, somewhere in between two stories, there's a middle story which has got weak. It's got a big columns, long columns. And the weak stories are very, very important to know. A weak story is what causes a building to fail, probably. And I've seen during our visit to Ahmedabad during the earthquake, we saw two very large buildings or very important buildings fail at the basement level, because the basement level had only columns with no in between partition walls. The upper floors had all of those with infill masonry partitions or infill masonry walls. So the upper floors were very stiff as compared to the ground or the basement, which was the parking level. And sure enough, that parking level columns just failed and the whole building came down. And there were examples of this type happening in that area during that Puja earthquake. Type 6 irregularity is not allowed in type for hospitals or post-disaster buildings, for example. That's the requirement. Okay, so what are the kind of restrictions and requirements that is related to irregularity? Either it is completely prohibited, as for example, type 6 irregularity is not allowed in hospitals, or if it's allowed, then design forces must be increased, or the design you may be asked to do the design on the basis of dynamic analysis, or maybe you want to do a nonlinear analysis. So those are the type of restrictions that the code specifies for different kinds of irregularities. And that's the table of irregularity. And I'm not going to go into detail of each one of these, but out of plane offsets, these are all defined in the code. But let me just talk about discontinuity in capacity or weak story. A weak story is one in which the story shear strength is less than that in the story above. The story shear strength is the total strength of all resisting elements of the SFRS, seismic force resisting system, who are sharing the story shear for the direction and consideration. So if you have a weak story somewhere, then it's very vulnerable, and type 6 irregularity attracts a lot of restrictions in the design. Torsional sensitivity is another one. Okay, finally, we talk about how do we analyze a building. And there are two methods of analysis, as you will see later on. Normally, you are asked to do dynamic analysis, but you can use equivalent static analysis in certain situations under the following condition. One of the following conditions. Structure belongs to seismic category 1 or 2. That means the risk is low. It is subjected to the DGM or the design ground motion is pretty low. Other structure is regular, is less than 60 meters in height, and has a fundamental lateral period TA less than 2 in each of the two orthogonal directions. If all of those conditions in the second bullet are satisfied, then you can use an equivalent static method for analysis. Or if the structure has irregularity type 2, 3, 4, 5, 6, or 8, but is less than 20 meters in height, it's short building, and has a fundamental lateral period less than 0.5 seconds in each of the two orthogonal directions. See, the short period buildings are safer. The long period buildings are not as safe. That's historically seen that the shorter buildings suffer less in earthquake because of reserve strength in the short period buildings. The other important thing is which direction is your loading. Wherever the components of the SFRS, the structure, the seismic force resisting system, are oriented along a set of orthogonal axes, you can do an independent analysis in each of these directions, each of these principal axis directions. If they are not so oriented, a set of orthogonal axes, and the seismic category is SC1 or SC2, independent analysis may be carried out by any two orthogonal axes. If you are not have a principal axis X and Y, but you have two orthogonal axes that you define yourself, you can do independent analysis along those two if the building belongs to seismic category SC1 or SC2. On the other hand, if it is not oriented along a set of orthogonal axes, and the seismic category is 3 or 4, structure should be carried out independently for two orthogonal directions, one for 100% and the other for 30%. And the two should be combined or added to get the final result for the design forces. And you can do X and Y, for example, 100% X plus 30% Y, or 30% X plus 100% Y, whichever gives you higher force in the structural element that you're designing. One final thing that we need to discuss, ductility related force reduction factor RD and overstrength related reduction factor RO. Whatever you have calculated on the basis of an elastic analysis for your force, the design force, you can reduce by a reduction factor RD to account for ductility, which means your structure will go into yielding, but it has enough capacity defined by that RD so that it will not fail. In addition, all structures have this reserve strength, which we cannot in an analysis account for easily, but they can be based on past experience and experimental evidence of the results reduction of the overstrength that exists. I mean, you have calculated strength on the basis of your standards and codes, but there is always some reserve strength in every structure. For example, if you're using a particular strength for your concrete, the real strength will be probably higher. Okay, so there are those reserves that exist, and these reserves can be quantified on the basis of experiments. So we use RO factor, which is the overstrength factor, that we use RD and RO. These are the two factors by which we reduce the elastic forces to get our design force. And we show, for example, this is a table of RD and RO for different structural systems, from ductile moment resisting frames for steel, and then go on to other types of structures, concrete, for example. And RD varies from 5 to 1 for steel, for example, RO varies from 1.5 to 1.0. So if you are ductile moment resisting frame, then you can use your elastic force and divide it by 5 and divide it by 1.5 as well to reduce to the design force, because there is ductility in that system, there is overstrength in that system. And then, of course, it also gives you some restrictions on the height. No limit, NL stands for no limit. And other figures, for example, limited ductility moment resisting frame will have allowed height if it's in category 3 of 60, no more than 60 meters, no more than 30 meters if it's category 4, and so on. If it's NP, it's not permitted. That's the situation there. So that table, which continues here. So let's now we are ready to now discuss the analysis procedures. We have defined what is RD, the ductility factor. We defined what is RO, the overstrength factor. We talked about W and IE and S, but there is something more here which we'll talk about. Okay, the specified earthquake base shear obtained, which is assumed that the building vibrates in a fundamental mode, is simply STAW. S you obtain from your hazard curves, the uniform hazard spectra, and W is of course the total weight of the building. So that's the base shear if it is vibrating in its fundamental mode. Now, of course, the building is not vibrating in its fundamental, it's vibrating in a combination of modes, and those of you who have some background on dynamics of structures would know what are the different kinds of modes. If there are different kinds of mode, then you have to account for those modes vibrating together. Then you have a factor called MV, higher mode factor, and it's given in table 7 later on. RD, as we have also discussed, is ductility, and RO is the overstrength. So the simple is you take the the fundamental mode value STAW. You have to modify it to make it less by RD and RO, because you have ductility in your structure and there's overstrength in your structure. And then if you have higher mode contribution, of course, most buildings will have higher mode contribution, you multiply by MV. So that gives you the final design base shear. Okay. From the simple value here to be modified by ductility factor, the overstrength factor, and multiplied by both the importance factor and MV, the higher mode factor. Now, one can see that you can similarly call this that IE. You can bring it here and make RD over IE, which is the same thing. And that's how the Indian code defines it. They put this IE in RD over IE or R over IE, which means you are relying less on ductility. In other words, whenever you multiply by I on the numerator, it really means you're reducing, or you're not depending on the full ductility, but you're reducing the demand on ductility by RD divided by IE. MV is the higher mode factor, RD is the ductility factor, RO is the overstrength factor. There is a limit to what you can go for walls, coupled walls. You should not go less than 4-second value. Okay. For moment resisting frames and base frames, you should not go less than 2-second value. That's the lower limit of what you can use in your design value. So instead of using the real TA, you can use whatever is less than 4, it's okay. But if it is more than 4, then just use the value at 4, no less than that. You know, as it reduces as the period becomes longer and longer. So the minimum value is at S 4.0 for walls and wall frame system. In certain cases, we can also have an upper limit, 2/3 of S.2 or S.5, upper limit, whichever is greater of these two. And this is because The upper limit comes when the building is very short, okay, 0.2 seconds. And there, in that short period buildings, there is a lot of strength which is unaccounted for. And it has been seen in the past that the short buildings or low period buildings perform much better in earthquake than the long period buildings or the tall buildings. And we are now comfortable in reducing that or putting an upper limit on this by using this factor 2/3 and or one of these factors. The upper plateau truth is applied in recognition of the fact that short period structures have been observed to have sustained less damage during past earthquakes because they possess extra reserve strength. The upper plateau is at 2/3 of S.2, but you cannot go lower than S.5. Okay. And I'll show you this again later on just to clarify what that means. You need a fundamental period. How do you got that TA? If you're using equivalent static force method, you don't want to be doing dynamic analysis, and therefore you don't have a period calculated for which you need a dynamic analysis. So what do you have? You have empirical expressions to find a TA. And these are the empirical expressions for steel moment frame, for concrete moment frames, for other moment frames, for braced frames, for shear walls. These are all based on height. Empirical equations best fitted to the real calculated values. And the other factor that we need is what is called MV, the higher mode factor. And these are tabulated also in the code, in table number 7 here. Depends on the value of the ratio of S at 0.2 to S at 5.0. And this can be 5, 20, 40, or in between. And for different periods, MB for 0.5 seconds and less. So you have to do 2 interpolations, one this way and then this way. One for this ratio and next time for that ratio. This is for moment resisting frames. This is for coupled walls, for example. So all the MB, and we'll talk about J factor in a short while. So the higher mode factor MV is calculated from these values given in this table. Okay, so we found out the base shear. How do we distribute it across the height of the building? First of all, we take a part of that V, and we call it FT, force at the top level, top of the building. And the value of FT is also given empirically 0.07 TA into V, and so on. And the remainder, when you take the FT out of V, that's V minus FT, the rest of the shear is distributed along the height of the building. So at the very top, there is this distributed value, Fx, but also there is Ft. But other floors is just the Fx. So Fx is how much? Is V minus Ft, which is the remainder of the V, multiplied by these values. Wx, the weight at level x, and the height of level x, and then the summation of this weight times height for all of the floors. So that's the Fx value at any level x from 1 to the top. Okay. At the top, of course, you have an additional Ft. Then we do the overturning moment. Now, you know, if the overturning moment is normally, of course, Fi times the force at any level multiplied by the difference between the height of that level and the height at which, and the point at which you want to calculate the overturning moment. This is the point X, or where you want to calculate the overturning moment. I's are the heights which go from X to N, from the level X to the top level. That would be normally the one which is there. Now, we want to reduce it. Why? Because you remember all of these forces, this particular expression that we just said is based on the first mode. Since our values are not just first mode, there are different modes at the same time. So this is over calculation. That's too much we need to reduce that. And there's a reduction factor that's allowed and is given in the code in the previous table that we talked about. This gives you the J values as well, MB and J values again. So you reduce this overturning moment by Jx using the value of Jx here. 1 for Hx that greater than Hn. Jx is J. J is the base overturning moment reduction factor given in that table, which is table 7. And finally, we have done all of our calculations. We found the base shear, we distributed across the height, and we found out the effect of overturning moment, the effect of ductility, and the effect of upper modes. There are the final things that we need to talk about is the torsional effects that exist along with the forces that we have. These forces just cause the shear and the horizontal forces. But there are torsional moments that exist for two reasons. If the center of mass and the center of resistance are not in the same line, there is a torsional moment. Okay. Because the forces exist through the center of mass and the building rotates about the center of resistance. There are also torsional moments due to accidental eccentricities. Even if we know center of mass or have calculated the center of mass and the center of resistance, we may be off in a building. Building might have eccentricities which we cannot know because the seismic structural stiffness is different than what we assumed, or it has deteriorated. So there is always going to be some accidental values which we miss. So there is a certain specification within the code gives you how much is that accidental existence which you have missed. It's not just what is caused by the difference between the center of mass and center of resistance. It is over and above that because your center of mass is not properly calculated. Your center of resistance is not properly calculated. The center of mass has changed because of you shifted all your luggage here and there. So there is always some unknown in that, and that's called accidental eccentricity. We will not go through the details of how that torsion is then accounted for. That's too much of detail, so I will skip that for the time being. So that's the equivalent static load method. The final one is the alternative method called the dynamic analysis procedure. You can use either one of these methods. You can use a linear dynamic analysis using the modal response spectrum method or the numerical time history analysis method. Or you can do a nonlinear dynamic analysis, which is a special study and requires special analytical tools and skills. So the modal response spectrum, of course, we need spectral acceleration values. These are the same values that are given in your UHS, the Uniform Hazard Spectrum, ST. If you have a linear time history method, then you need ground motion history. And you need to create these time motion histories which are compatible with the response spectrum. And those of you who have this expertise in finding out ground motion time histories know how to create these time histories so that they produce the same spectrum as you have in your design. Then you have to account for the effects of accidental torsional moments and the other moments that are caused by the earthquake forces. And that is based on those details that we skipped earlier. Okay, so you find out adjust the elastic value. You divide it by RD RO multiplied by IE to get your design value. Okay, so far so good. Then you can do a little bit of trick here. You can put this upper limit, just as we did in the equivalent static load method, 2/3 or S.5. That is, if the period building is less than 0.2 or 0.5, you get these upper limits, which is based on the observation that the short period buildings have got much reserve strength. And these values that you got, of course, have to be multiplied by importance factor IE and be divided by RD and RO, just as we did in the case of equivalent static method to find out the final design values. Give you the specified lateral earthquake force, which is your design value, VD. Okay. Now, VD should never be less than 0.8 V, as we determined from equivalent static load method. You probably VD will be smaller than V, that you found from V, from your equivalent static load method. Capital V is the one which you found from equivalent static load method. VD is what you did from your dynamic analysis, and you usually will get lower than that. But you cannot take less than 0.8 V. Why? This is because when you're doing a dynamic analysis, you are modeling a structure, and you are not able to determine the effect of certain stiffening agents there. Okay. So your period, the dynamic period, is longer than the real period because the building is really stiffer than what you thought because of, say, shear walls or infill walls of masonry or other reasons. The building is really stiffer than what you thought in your dynamic analysis. In your dynamic analysis, you're not able to represent every structural system that is taking part, and therefore you should not go too far from the equivalent static load method. Therefore, there is a limit of 0.8 V that the code prescribes. Irregular structure, not even 0.8 V, full V. Once you determine that VD and VE, then you can revise your forces in the individual elements of the structure, and you get that. Sorry, skip that. Yes, we back to the uniform hazard spectra, and you see the upper cap. By 0.2 or 0.5. This is 0.2 or less. This is now becoming 2/3 after that. So that's the upper cap. But you should never go, of course, less than what is required for 0.5. 0.5 is this one. Yeah. So we were at the very end. Go to the last slide here. Okay, so we were on dynamic analysis procedure. That's Article 12, 4.1.8.12. The code doesn't end there. It has got certain more articles, as I said, from 13 to 23 more. And it has got these definitions in these articles. Article number 13 gives you the drift limits, the deflection limits, how much structural separation you need between two buildings, design of diaphragms, collectors, cords, struts, and others, foundation provisions, site stability, non-structural components and equipment that is housed in the building. Then we need to talk about isolation, which is a special case, and we are not going to discuss this in this particular talk. But this is a very interesting thing. There is also called supplemental energy dissipation systems and additional performance requirements for post-disaster buildings, high importance building, and some normally. The seismic isolation is an interesting thing. As you all probably know, that it has been used in many buildings. What you do is you put ball bearings type of isolators between the structure and the foundation. So any column that is coming down, it stops somewhere, and then you put these seismic isolators or ball bearing type things, and you go down to the foundation. So what happens is the foundation moves with the earthquake. The building doesn't move as much because of these isolators, which are like ball bearings. And they separate the upper building part to the lower building part. And I wanted to just say a few words about this because right now in Canada, I mean, seismic isolation has history. Not many buildings in Canada have been put on seismic isolators, except a couple of them. US has got some more. Japan has got thousands. And Turkey has now some for particularly hospitals. So right now in the Parliament building of Canada, which is located in Ottawa, it's an old building, 1910, and built in 1910. Heritage building built of beautiful masonry structure, and we don't want to touch it. I mean, as long as possible, we don't want to change any structure within that, on the walls or the columns. So what do we do in an earthquake? How do you prevent that thing happening? You know that there is a weakness in the columns, a weakness in the shear walls. You want to retrofit them, but then you're touching the heritage nature of the structure. You don't want to do that. So what you do is you put the whole building in ball bearings on isolators. And right now, the center block of the Parliament building of Canada, which is located in Ottawa, is undergoing a seismic renovation or retrofit and using seismic isolators. There are in all about 460 isolators which are distributed between the columns which are bearing the load and the foundation. So what you do is let's take each column at a time. You first of all jack up the column from the sides, so you relieve the load from the column, bring it into the jacks, then cut the column at the base between the foundation and the base, and you insert these isolators. And once you insert the isolators, you gradually lower the building or take the jacks down, so the column now starts to rest on these isolators, which are running between the foundation and the upper part. So what happens is, when you have an earthquake, the foundation moves, the building stays still, but there is a relative motion between the foundation and the building, obviously. So we create what is called a moat all around the building, so that there is space for the foundation to move to the left, the building standing there, or you can say the building is moving relatively to the right, so you need a space there. So that's why it's going on. It's a long process. The building will supposed to be completed in year 31 or so, 2031 or 2030. It's a 10-15 year project which is going on right now. So that's an interesting project, but that was not part of my presentation here. I just wanted to mention that that's something in progress here, right in Ottawa. So I think that sort of summarizes what I was going to say about the National Building Code of Canada. And if you compare it with the National Building Code, the Indian National Code for Earthquake Engineering, there are many similarities, but there are also differences, of course, in how each detail is being handled. It will be interesting to compare the relative values of the earthquake hazard in the two countries. And I generally found that it is much higher in Canada. In the highest zone, for example, compare the highest zone in India, one can compare the two, and you can see the values. For example, in India, it's the Z by 2 multiplied by SA, and that will be compared with the uniform hazard spectrum that the Canadian code gives, and there will be a comparison of the two. So thank you so much for listening, and I'll try and answer any questions that you might have. So I'll stop sharing my screen at this time.
So,
okay, yeah.
Thank you, Professor Huber, for giving such a excellent presentation. And now, of course, we in India also making changes, and then our latest code on earthquake resistant would be published very soon, where we will also take care of the type of importance vis-a-vis the return time period. I mean, those
Yes, sir. I think there is internet connection problem.
Some freezing is there. Yeah.
Yes. So there are 3 questions in the Q&A box. Can I ask?
Yeah, sure.
Yes.
collapse. So, I mean, what is the mode of resistance, the design that we see?
Hello, Dhawan sir, your internet is not stable. Please ask the question again.
Yeah, I am not able to understand, so maybe.
Second question is this modeling. Soil structure interaction also is a part of your modeling.
Yes,
and then
there is a very extensive provisions on soil structure interaction. We didn't go into that, but yes.
Then foundation provisions and then site stability. These are
those are also included in the code, as I mentioned, between sections, articles 13 onwards. 12 is the dynamic analysis method. From article 13 to 23, the remaining part of the code, which I did not discuss, has the soil stability, site stability. It has got isolation. It has got supplemental energy dissipation and other things that I did not talk about. Yeah, which has got some provisions. Of course, most of these are special studies are required, and you need some expertise over and above what you can normally find in a code. So design of isolators, for example, is very specialized.
Because
yes, sir. Yes.
Why is it audible? Please continue.
Yeah, so there are a few questions, sir. First, Mr. Krishna asked, if ground is prone to liquefaction and pile foundation provided to transfer load to firm strata rock, what is practice in Canada on magnifying spectra with FA and FE as in NBC? IBC.
Okay, so yeah, the liquefaction is being dealt with in the code, and it provides what is required to be done in adjusting the forces in a liquefiable soil. But the pile foundation not clearly defined in the code, but in the foundation design manuals, you will have that. So that is the topic has to be gone into that. But both of them are defined in either in the seismic code or in the related codes of other type. The codes for soil structure interaction, for example, for liquefiable soils, and for foundation, some part of it is also in the code, as I mentioned to you, between articles 13 to 23. There's some relation to foundation as well.
Yes, sir. Mr. Sunny asked, what is X450? As I have seen in some articles.
Yeah. If the shear wave velocity in the top 30 meters has been measured at 450 meters per second, that's called X450. So anything that you see X450, any value that corresponds to X450 is when the site has been measured to have a shear wave velocity and average value of 450 meters per second. Similarly, X760, which is class C, really almost like class C, a medium type of soil, is 760 meters per second. That soil will be classified as X760. And when you try to find out the seismic hazard at any point, say for example, if your soil has a shear wave value of 450, then in that tool that I showed you, you put the value of X as 450. So it will become an X450 soil. And for X450, it will produce the hazard values. If you have a 760, you put 760 in that, and you get the hazard value for 760 meters per second shear wave velocity soil. So depending on your site, you must have a shear wave velocity measured in the top 30 meters. The average value of that shear wave velocity will determine the hazard. And so the tool takes care of that. The seismic hazard tool, which is the link that I provided, will automatically take care of, once you tell that tool what's the value of X. Is it 450? Is it 760? Is it 1000? Or it's 150? So depending on that value, it will automatically calculate the value of the hazard. And hazard, of course, varies depending on the site property. So the very stiff soil or the rock, the hazard is lower. And it automatically determines that for every kind of soil. So you don't have to go to discrete values where we classify soils normally as rock, hard rock, rock, stiff soil, medium stiff soil, low value soil, and then you get values for those hazards. But this particular tool will give you the value for any value of your shear wave velocity. If you have the shear wave velocity measurement, if you don't have, then you have to use those classes A, B, C, D, E, F. It will provide you the hazard for each of these classes. So X450 simply means that the site soil that you have has a property which gives you a shear wave velocity of 450 meters per second average over the 30 meters below the foundation.
Yes, thank you, sir. Dr. Satish Sharma asked, IS 1893 specifies the maximum value of SA/GS 2.5 in your view. Should this value be upgraded in view of many earthquakes of higher accelerations in the recent past?
Well, the 0.5 value that you have, I think you have a 2.5 as n to z by 2, of course, that's the value that you have. Now that value is supposed to be based on past earthquake observations. And that's the value that is normal building will have to experience. Now, should we modify that value? Yes, if for irregular buildings, for example, there is a modification proposed, you have to design for a higher value, so on. That can be done in two ways. Either you reduce your RD divided by IE, for example, or you choose a lower value for SA. So yes, for liquefiables, for poor soils, you use a different value, and you have to reduce or increase the value depending on many other factors, like irregularity, for example, is one of them.
Yes, thank you, sir. Mr. Sunny asked, which is the best book to understand the NBCC 2015 or 2020 provisions for steel and concrete?
Okay, the best thing is to look at the commentary of the code. Of course, dynamics books will not give you exactly the code values, code discussion so much. But if you have the dynamics, the background is needed. But the best place to find out is the commentary. There is a commentary accompanying every code cycle. So there is a commentary accompanying 2020 NBCC 2020, and that commentary will explain enough for you to be able to make some judgment values. For each article, it gives you a commentary. How is that article related to the design, or what's the basis of that article? So that's the best place to study. Now, commentary is accessible either online or you can buy it on, probably, I don't know whether Amazon has got it or not, but the National Building Code of Canada, wherever you can get the code, you can get the commentary as well.
Yes, so thank you, sir. Mr. Lakshmi Narasimha Rao asked, for structures which have two-factored analysis, like 3-story timber, steel building, or different RDRO, over concrete slab with concrete shear walls, what would be connections of SFRS system at this slab be designed for?
I didn't understand. What's the connection of the
connection of SFRS?
Oh, SFRS. Yeah. Two different SFRS. One you mentioned was wood, and the other was concrete. Okay, each SFRS that you provide in a structure has got its own RD value and RO value. That's one major thing. Ductility capacity and the overstrength of that particular RD or for that particular material. And there is a table which provides those values. Depending on what kind of material you're using, you have a different RD value by which you can divide your force. Which means if you have a more ductile system, for example, a steel structure with properly designed steel sections has a higher RD value than a masonry structure would have. So you can reduce your structural design force by RD, that higher RD, depending on the type of material that you have. So that's the role of RD. RO is a similar role. Some structures or some material types will have greater strength, greater reserve strength. A beam of concrete, for example, might have a greater reserve strength than the beam made out of timber structure. So these are different type of materials, and mainly depends on the type of material you have and the type of structural system. Is it a column or a beam, or is it a wall? So based on these, you can determine the value of RO, which is based on experimental evidence from past. And these RO values are tabulated in the code for each type of structural system. You use the proper RO value and similarly the proper RD value, so ductility and overstrength. These are important. If you have both of them, you can reduce your elastic force by these RD and RO.
Thank you, sir. Dr. Subramaniam Narayan sir asks, I heard somewhere that equivalent static method of analysis gives good results in regular buildings. Is it true?
Oh, the equivalent static load method is good for regular buildings. It's not good for irregular buildings, and the code really defines that irregular buildings of certain types will need dynamic analysis. In fact, some of them might need even a non-linear dynamic analysis, depending on the type of irregularity you have. Yeah. So irregularity means you have to have a stricter method of analysis, because normal equivalent static load method will not work in a building which has got, for example, a weak story or an offset or a changing stiffness, drastic changing stiffnesses, different kinds of irregularities that are defined in that table. Any one of those will produce a building which is difficult to find the analytical value by using equivalent static load method, in which case those are prevented. That's number one. Number two, if it's a high risk building, that means if you belong to very high value of the hazard spectrum, then again you have to be very careful that you do not use the equivalent static load method, because under high values of those, there is a higher risk or a higher vulnerability. And that's also clearly defined under what circumstances you can use the equivalent static load method. There are certain restrictions under which you can use. A regular building, yes, there is every chance that you will be allowed to use. If irregular building, there may be restrictions on whether you use, is it tall building, is it short building? Those are some of the risk factors that are there. Depending on that, you can use one or the other method. And so code very specifically lays down the situation in which you can use the equivalent static load method. And when I say code, it's the National Building Code of Canada, which has got these restrictions laid out. And it was part of the presentation. So when you get this, the recording, you will be able to note that.
So Mr. Amit Gupta asked, what are importance factors and RD and RO for very important structure like concrete gravity dam?
The importance factor depends on not the type of material, but the type of use that you are using building. A normal building has got, for example, IE of 1. Okay, normally is 1. But if you have a post-disaster building like a hospital, your IE is 1.5. So the importance is 1.5. Now that really means that you're designing for a higher force, which means less ductility is required. Okay. Because you're not expecting the structure to become ductile. You're designing for a higher force, which will keep the building elastic during the earthquake. The higher the IE value, the less chance of it becoming ductile or yielding. So IE is the factor which depends on the function of the building. A hospital has to remain functional after a disastrous earthquake, after the design earthquake. And therefore, you use a high importance factor, which effectively means you are using RD divided by IE. So using a less RD. You can either say you multiply by IE, or you say, okay, instead of dividing by RD, I'll divide the whole thing by RD less by IE. So if IE is, for example, 2, your RD is 4, then you should be, when you are multiplying by 2, it really means you are making your RD demand as 4 by 2, which is 2. So both are related to each other. The importance factor depends on the function of the building. Yeah. Okay.
That's
Yeah.
all?
Yeah.
No, sir. There are few questions. There are few questions more. Sir, Mr. Sunny asked, what if the structure is designed using NBC 2015 and is failing while checking with NBCC 2020 seismic parameters?
Yeah, okay, yes, that's right. That's a good question. Now, you design old buildings which have been based on previous codes, and the 2015 is the only one. The 2010, there is a 2005. So you go back sometimes 2005, and you are in 2020. So what kind of restrictions are there? Now that depends on each, what we call as the jurisdiction or the municipality or the province or the state in which you are located. They might give a special regulations that, okay, all buildings have to be upgraded to 2020, or certain class of buildings have to be upgraded to 2020. For example, heritage buildings like the parliament that we were talking about, we want to upgrade it to the latest one, 2020, let's say. It also depends on, because it will this means cost effective. Now you cannot ask every owner of a building or a residence, for example, you have a home which was designed, which is in an earthquake prone area, and you designed it for the 2005 code, and now you're in 2020 or 2015, and you want to upgrade it. If you are required to do it, you have to spend money. So the municipal area in which the building is located has to weigh these factors and decide whether in our area we want everybody to upgrade it to 2020. Mostly no. But in some types of buildings, you may want to. Buildings which are critical for you, buildings which are hospitals, for example, you may want to do it. A power plant, for example, you may want to upgrade it to the latest code, knowing that yes, the latest code is higher than the previous code, then you need to do it. So it's not a universal thing. It's probably mostly based on surveys that the jurisdictions do to determine how much the cost-benefit ratio, how much is the risk involved, and so on.
So thank you, sir. Mr. Shashi Shekhar asked, question one is Canadian code considered the effect of redundancy and damping in R, like over strength and ductility? And his second question is, in place of normal concrete, if fiber reinforced concrete, how to calculate R and how to limit the parameter of R calculation if no practical data is available for FRC?
That's a good question. There is whole guidance given in some of these FEMA documents about how to go about determining the values of R for type of structural systems that are not included in the code. Maybe every time you come up with a new structural system, sometimes you have to define what's the RD and RO. And so there is a series of methods of doing that. There is a whole document that's published. I don't remember the number of that, but how RD, ROs are determined. And for example, when we went to the 2020 code, we redid most of the RD, RO calculations to see whether they comply with the latest methods that are around for determining these values of RD and RO. These are mostly based on experimental evidence for the type of structure you have, the type of material you have, and there are specific methods of how you determine these values. And the best way is to get to this to find this structural publication on that one. And that will give you the details of how to determine. We have a group within our code committees doing exactly that for some type of structure, certainly.
Yes, sir. The question Mr. Sachin Oak asked, I did visit the Senate building in Ottawa last week. For such long-term projects, are the changes in the code applied along the construction period? Example, the Senate building work might have started before NBCC 2020 came out. So will this code be applicable to the construction?
No, not necessarily. If the building started being retrofitted or renovated, for example, in 2018 or 2017, and you now come to a 2020 code in between the start and the finish, you don't want to go back and change that. No, it's not necessary, unless there is special circumstances. The renovation design which is approved by the municipality or the authority having jurisdiction is based on the day you applied for that permit. Okay. So if you said, for example, I said, okay, this is my design for my retrofit for this particular building, and you submit it to your municipality or the jurisdiction authority, you approve my design. I have stamped it, you approve it. They will approve it on the basis the comparison of the existing code at that time, unless there are some special reasons. So you don't suddenly change your design when the building is going over a period of time, you're doing the retrofit. Yeah, that's not practical. And except in special situations, you just have the approval done at the start of your renovation. When you produce your drawings, you produce your design. So this is the design based on the current value of the current version of the code at that time.
Yes, so thank you, sir. Dr. Padmaja Gokaraju asked, what type of analysis is suggested to steel industrial buildings as per NBCC 2020?
What kind of analysis for industrial buildings?
Steel industrial building.
Pardon, which kind?
Steel
structure. Steel structure industrial buildings.
Oh, steel structure buildings. What kind of
Industrial
analysis?
building.
Oh,
Yeah, what type of analysis?
Industrial building.
Industrial building, okay. Yeah,
Right.
well, industrial buildings, well, if you have irregularities in the industrial building, if an industrial building which is straightforward, regular building, you can use the equivalent static load method. It depends on whether it's industrial or normal, makes not the difference really. It's the type of structural system that you have, the regularity in the structural system, the other things, factors that we mentioned, that will determine whether you can use one or the other method of analyzing the structure. So if it's industrial, that doesn't really make a difference. Now, the only thing that might make a difference is, for example, if you have a chemical factory producing chemical toxic elements. Okay. Now, that is a vulnerable thing because you don't want it to yield or to fracture or to have cracks. And then you may want to say, okay, for this particular type of building, I want to do a nonlinear analysis. So that's the risk involved in a particular building's failure or going into cracking or yielding. That's where you have either the importance factor determined or you have the type of analysis that you want to do. So that's the reason that you might choose a different way for the industrial building. There are certain types of industrial buildings, for nuclear power plants, for example. You don't want any release of toxicity. So you don't want big cracks. You don't want yielding. You have a different way of designing. Okay.
Yeah, thank you very much, sir. These are the only questions.
Professor, on behalf of IAStructE and my personal behalf, thank you very much for sparing valuable time and sharing your long experience in the structural design. I mean, we organize such lectures every month for the benefit of our young structural engineers. So thank you once again.
Well, thank you, Dr. Dhawan. This is on your behalf that I want to thank. everybody and you yourself particularly, but giving me the privilege to speaking to the enlightened people across India, and it's a very unique opportunity to be talking about this. We were recently in India, of course, and that's just a visit. But the big visit that I recall is the earthquake time that we went to there to examine the Gujarat
That Bhuj
province.
earthquake. That Bhuj earthquake time you must have.
Bhuj earthquake. Yes, that was a very interesting with a team of Canadian delegates. I was leading the team, and we had a good visit to all of the areas in Gujarat, including Ahmedabad, of course, but Bhuj also. Looked at a hospital which was destroyed completely. We looked at an area where the kids were marching, the buildings came down. Yeah, there was a lot of learning that. Interestingly, I found with all of that loss and destruction that some of the multi-story buildings were subjected to. There are two multi-story buildings which just came down because the basement was open. The columns simply failed. But in the same town, there is a temple called Hati Singh Temple. Long past it was built in masonry, intact, no damage at all. So it was quite an eye opener, in fact. So, and of course, the major damage was because in the villages and the small towns, the type of construction they had was thatched or roof that was not properly attached to the rest of the structure, and the roofs came down. The people were sleeping at that time. The hospital, that was a big loss that in Bhuj. Yeah, that was
very sad.
Yeah, but we had a lot of learning from that, and but
I mean,
I found that
still you are looking like a student at the age of 87. It is just motivation to all young engineers to see you work hard and come up with better things.
India has a lot of skills and very advanced in the knowledge of the earthquake engineering. Sometimes that knowledge doesn't trickle down to the level of construction.
Yes, sir. That is a wide
other
gap.
than that, I think you are as good as any in the world.
No, but sir, there is a wide gap between the industry, the actual construction, and the design.
Yeah.
I mean, that is the particular durability part. Now everybody is trying to do the research in corrosion. In buildings in India also constructed during 50s, 60s, there have been no problem. So the durability part needs to be strengthened during construction. And this is what here from Indian side, this is my observations to the.
Thank you so much. Thank you for inviting me.
Okay, sir.
And
Thank you so much. Thank you so much, sir.
Thank you, sir. Thank you.
Thank you.